All right, so we're going to look at what's called, sorry, I went really quick. We're going to look at what's called the central limit theorem. And this lets us decide when we can use our sampling distributions to represent our population values. And so the central limit theorem has two parts. Firstly, it says if the number of samples, if the sample size, right, which is what we're using for n, is greater than or equal to 30, so if we draw from any population and the sample size is greater than or equal to 30, then we can say that our sample mean is a good approximation for the population mean, and our standard deviation of the mean is equivalent by that relationship. So what it says is no matter what the shape of our sampling distribution is, right? So that's our sampling distribution. Or I'm sorry, this is our population distribution, whatever the real value is of the population distribution, right? And it's going to have some mean value, and it's going to have some standard deviation. And if we take a large number, or an n number of samples, our sampling distribution is going to look like this. And so that mean and the standard deviation of our sampling distribution will be bell-shaped. But if our n's, if our samples are greater than 30, these two will talk about each other. And so the central limit theorem basically says, you want to know something about your population? Get more than 30 samples. And then the other thing it says is, well, there's another case, and that case might be that you know the population. You know the population is normally distributed. For some reason, the laws of nature will normally distribute it, or you have already measured it and you know it's normal. Then you know, no matter what the n is, no matter what n is, mu of x is equal to mu. The mean of your samples is equal to the mean of the population, and your standard error of the mean is equal to the standard deviation of your population, divided by the square root of whatever your n is. Two big things come out of this. For a better experiment, n must be larger, must be larger. But it only gets better as the square root of n. So let's say you have an experiment with 10 samples, right? To make it 10 times better, you do I apologize, 100 samples. So you have 100 samples. To make it 10 times better, right? So the square root of n is 10, or square root of 100 is 10. Sorry, I want to focus on 10. To make it 10 times better, I need the number whose square root is 100. And so I actually need 10,000 samples. And so I need to increase this by 1,000 times. And if I wanted to make it 10 times better from that, I would need something where I had 1,000,000 samples. And so to get better by powers of 10, we go up larger and larger and larger due to this square root of n. And so we need more samples to be better, but we need more and more and more to get successfully better. And so there's usually a medium round to go here. One of the kind of rules of thumb that I always heard was for something with a population of like 100 million or so, you need a couple thousand. For most things that you deal with, you only need that 40 to 50 of the central limit theorem. And also, when we say that the mean of your sampling distribution is equal to the mean of your population, we're actually saying it's approximately. And it becomes a better approximation, the larger n is. The larger, today is a spelling issue, larger n is. And that's the central limit theorem in a nutshell. It works out that we can find our way between these, between anything we measure and a population if it's normally distributed population, then these are great approximations for each other. If our samples are greater than 30, then we have the ability to approximate these things. If we don't know if it's normally distributed and we have less than 30 samples, we can't say this. Because what ends up happening in statistics is in general you try to take more than 30. You try to take more than 30. Or you focus on things that are normally distributed. Both of the things happen through and through. Alright, that is all of chapter 5. I will do examples based off of questions, but if you need anything, holla. Holla, holla, holla.